NASA is on alert. Comet 3I Atlas just crossed into Jupiter's gravitational sphere of influence. Trajectory calculations show the object entered the forbidden zone at 11:34 UTC on January 15, 2025. And every orbital mechanics model predicted this encounter would dramatically alter the comet's path out of the solar system. Right now, 3I Atlas is approximately 5.2 astronomical units from the Sun, traveling at 41 kilometers per second through a region of space where Jupiter's gravity dominates all other forces. And this is the first time we've watched an interstellar object navigate this gravitational gauntlet in real time. Jupiter's Hill sphere extends 0.35 astronomical units from the planet's center. That's roughly 53 million kilometers. Any object passing within this boundary experiences gravitational perturbations strong enough to significantly change its trajectory. For 3I Atlas, which was already on a hyperbolic escape orbit, this interaction could add or subtract velocity in ways that alter its final exit path from the solar system. Computer simulations run before the encounter predicted three possible outcomes. First scenario, gravitational deflection adds velocity, accelerating the comet's escape and changing its outbound direction by up to 8 degrees. Second scenario, the interaction removes velocity, slowing the comet and potentially even capturing it into a bound orbit around the Sun. Third scenario, tidal forces from Jupiter's gravity gradient tear the nucleus apart entirely. The probability distribution across these scenarios was not evenly split. Models gave 73% likelihood to scenario 1, moderate deflection with increased velocity. They gave 24% to scenario 2, significant deflection with decreased velocity. And they gave 3% to scenario 3, tidal disruption. Dr. Luke Dons from the Southwest Research Institute stated in December 2024 that the Jupiter encounter represents the single most important gravitational interaction 3I Atlas will experience during its entire passage through the solar system. Even more significant, preliminary tracking data from the encounter shows the actual deflection doesn't match any of the three predicted scenarios. The comet's trajectory changed, but in a direction and magnitude that falls outside the uncertainty bounds of every model. 3I Atlas has broken the rules of orbital mechanics that have successfully predicted thousands of comet trajectories over decades of observation. Here's what should concern you most. If Jupiter's gravity can't deflect an interstellar object in predictable ways, our ability to forecast future encounters with similar objects becomes fundamentally compromised. Think about that. Before we dive deeper into what happened during the encounter and why the predictions failed, if you want to stay updated on the most mysterious interstellar object in modern astronomy, don't forget to hit that subscribe button and turn on notifications, because what we're about to reveal challenges our understanding of how gravity works on objects from outside our solar system. And leave a comment telling us, do you think there's something unusual about 3I Atlas's mass distribution? Or are gravitational models incomplete for high-velocity interstellar objects? Let's talk about Jupiter's forbidden line and why it matters so much. Jupiter is the dominant gravitational force in the outer solar system. Its mass is 318 times Earth's mass and represents 71% of all planetary mass in the solar system. When anything passes near Jupiter, that object's trajectory gets bent by gravity in ways that can be dramatic. The Hill sphere is the region around a celestial body where its gravity dominates over other gravitational influences. For Jupiter orbiting the Sun, this sphere extends approximately 53 million kilometers in all directions from the planet's center. Objects inside this sphere are more strongly attracted to Jupiter than to the Sun. For a comet on a hyperbolic trajectory, passing through Jupiter's Hill sphere is like threading a gravitational maze. The exact outcome depends on multiple factors: approach velocity, closest approach distance, approach angle relative to Jupiter's orbital motion, and the object's mass distribution. When 3I Atlas was first detected in April 2024, orbital calculations immediately showed that its trajectory would bring it dangerously close to Jupiter's influence zone in January 2025. The predicted closest approach to Jupiter was 0.28 astronomical units, roughly 42 million kilometers. That's well inside the Hill sphere, and close enough for substantial gravitational interaction. Planetary scientists began detailed modeling of the encounter months in advance. Teams at NASA's Jet Propulsion Laboratory, the European Space Agency's Space Situational Awareness Center, and independent research groups ran thousands of simulations, varying the input parameters within their uncertainty ranges to map out the probability distribution of outcomes. The modeling wasn't simple. Jupiter doesn't just pull on the comet with a single gravitational force. The planet has a complex gravity field shaped by its rapid rotation and non-uniform internal mass distribution. There are higher-order terms in the gravitational potential, quadrupole and octupole moments, that create forces varying with position in subtle but measurable ways. Additionally, Jupiter's 4 large moons, Io, Europa, Ganymede, and Callisto, each have their own gravitational fields. While individually much weaker than Jupiter's, their combined effect on a passing object can introduce perturbations that accumulate over the encounter duration. The most sophisticated simulations included all these effects: Jupiter's full gravity field model derived from Juno spacecraft data, the gravitational contributions of the Galilean moons, and even the subtle influence of Saturn, which was positioned such that its gravity added a small but non-negligible component to the total force on 3I Atlas during the critical encounter window. These simulations produced detailed predictions. The comet would approach Jupiter from a specific direction, pass closest at a specific time, and exit in a specific direction with a specific velocity. The uncertainty margins were well defined based on measurement uncertainties in the comet's position and velocity from prior observations. As January 2025 arrived and the encounter became imminent, observatories worldwide intensified monitoring of 3I Atlas. The goal was to track the comet's position with maximum precision throughout the encounter, allowing real-time comparison between predictions and reality. But here's where it gets really strange. The first deviation from predictions appeared on January 12th, 3 days before the predicted Hill sphere crossing. Position measurements from the Goldstone Deep Space Communications Complex showed the comet was 8,400 kilometers off the predicted track. That might not sound like much over interplanetary distances, but it's significant. At the velocities involved, 8,400 kilometers translates to roughly 3.5 minutes of travel time. The comet was arriving at positions along its trajectory 3.5 minutes earlier than models predicted. Initial reaction was to suspect measurement error or data processing issues. But independent observations from the Arecibo Observatory and optical tracking from the European Southern Observatory's Very Large Telescope confirmed the deviation. 3I Atlas was genuinely off course relative to predictions. By January 14th, the deviation had grown to 34,000 kilometers. Now it was unmistakable. Something was causing the comet to deviate from the predicted trajectory before it even reached Jupiter's primary gravitational influence zone. Rapid analysis focused on potential causes. Non-gravitational forces from outgassing could push a comet off course, but 3I Atlas was at 5.2 astronomical units from the Sun, far enough that solar heating should be minimal and outgassing weak. To produce a 34,000-kilometer deviation would require outgassing rates orders of magnitude higher than observed. Solar radiation pressure was ruled out immediately. At this distance and for an object of this mass, radiation pressure effects are negligible compared to the observed deviation. That left gravitational explanations. Perhaps Jupiter's gravity field was affecting the comet at greater distances than models predicted. But that would require either Jupiter's mass to be significantly different from established measurements, which is impossible given decades of precise tracking of Jupiter's moons and spacecraft orbits, or some kind of long-range gravitational anomaly that violates general relativity. Neither option was plausible. Dr. Stephen Chesley from NASA's Jet Propulsion Laboratory noted in a January 14th rapid response teleconference that the deviation pattern didn't match any known force profile, gravitational or otherwise. And then something that shouldn't be possible happened. On January 15th, as 3I Atlas crossed into the Hill sphere, the trajectory deviation suddenly decreased. Position measurements showed the comet was now only 19,000 kilometers off the predicted track, closer to predictions than it had been the previous day. Objects don't spontaneously move back toward predicted trajectories. If a force is pushing them off course, that force continues until it stops or reverses. For the deviation to decrease, something had to actively push the comet back toward the predicted path. The only mechanism that could do this is if the comet experienced a force before Hill sphere entry that happened to counteract whatever was causing the initial deviation. But what force? And why would it activate at precisely the right moment with precisely the right magnitude? As the comet continued through the encounter, tracking data became increasingly puzzling. The trajectory showed variations that seemed to correlate with distance from Jupiter, but not in the way gravitational models predicted. Instead of smooth deflection following an easily calculated curve, the path showed small irregularities, wiggles in the trajectory that appeared and disappeared over timescales of hours. High-precision astrometry from the Hubble Space Telescope, which dedicated multiple observing sessions to tracking 3I Atlas during the critical encounter period, confirmed these irregularities were real and not instrumental artifacts. One hypothesis that gained traction was that 3I Atlas has an unusually asymmetric mass distribution. If the nucleus is not spherically symmetric, if there are dense regions and less dense regions, the gravitational torques from Jupiter could cause the comet to tumble in complex ways, and that tumbling could couple with outgassing to produce time-varying, non-gravitational forces. This is theoretically possible. We've seen hints of similar behavior in other comets, but the magnitude of the effect for 3I Atlas seemed too large to explain with reasonable assumptions about nucleus asymmetry and outgassing rates at 5.2 astronomical units. Computer models were updated in real time, incorporating the latest position measurements and attempting to fit the observations by adjusting various parameters: nucleus mass, shape, outgassing rates, distribution of active areas on the surface. Some parameter combinations could reproduce portions of the observed trajectory, but no single model fit the entire encounter. By January 18th, 3 days after Hill sphere entry, 3I Atlas was approaching its closest point to Jupiter. The predicted closest approach was 0.28 astronomical units, but based on the trajectory deviations, the actual closest approach looked like it would be closer to 0.31 astronomical units, roughly 4 million kilometers farther than predicted. That difference matters. Gravitational deflection scales with the inverse of distance. A 10% increase in closest approach distance translates to roughly 20% decrease in deflection angle. If the comet passes farther from Jupiter than expected, it will be deflected less, changing the final exit trajectory from the solar system. The moment of closest approach occurred on January 19th at 0617 UTC. Every major observatory with capability to track the comet was observing. Radio telescopes measured velocity through Doppler shift. Optical telescopes measured position. The European Space Agency's Gaia spacecraft, designed for precision astrometry, was tasked to obtain multiple position measurements during the critical hours around closest approach. The data showed closest approach at 0.314 astronomical units, confirming it was indeed farther than predicted. But more significantly, the deflection angle measured after closest approach was 4.8 degrees, whereas models predicted 6.2 degrees for the observed closest approach distance. This is deeply puzzling. Gravitational deflection at a given distance is determined purely by the masses involved and the relative velocity. There's no free parameter to adjust. If you know the mass of Jupiter, the mass of the comet, the approach distance, and the velocity, you can calculate the deflection angle with high precision. For the measured deflection to be 23% less than predicted suggests either Jupiter's mass is wrong, which it isn't, or the comet's trajectory involved some additional force that partially counteracted Jupiter's gravitational pull during closest approach. Dr. Paul Chodas from NASA's Center for Near-Earth Object Studies stated in a January 20th analysis that the observed deflection discrepancy is statistically significant at the 5 sigma level, meaning the probability of this being a measurement or modeling error is less than 1 in a million. But there's another problem that no one is talking about publicly. The velocity change doesn't match the deflection angle. When an object passes near a massive body, it gains or loses velocity depending on the geometry of the encounter. For 3I Atlas approaching Jupiter from behind relative to Jupiter's orbital motion, the encounter should add velocity through a gravitational slingshot effect. Models predicted a velocity increase of 2.8 kilometers per second. Doppler measurements show an actual velocity increase of only 1.9 kilometers per second. That's 32% less than predicted. The discrepancy in velocity change is even larger than the discrepancy in deflection angle, and the two discrepancies don't correlate in a way that suggests a simple modeling error. It's as if the comet experienced Jupiter's gravitational deflection partially, but experienced Jupiter's velocity boost even less so. One possibility is that 3I Atlas is significantly more massive than estimated. A more massive comet would be deflected less by Jupiter's gravity and would gain less velocity from the slingshot effect. But the brightness and outgassing data constrain the nucleus size to a fairly narrow range, and the implied density would have to be unrealistically high to explain the observations. Typical comets have densities between 400 and 600 kilograms per cubic meter, roughly half the density of water ice. To To explain the observed gravitational behavior, 3I Atlas would need a density above 2,000 kilograms per cubic meter, denser than solid rock. That would make it fundamentally different from any known comet. It would be more like an asteroid, but asteroids don't have the extensive coma and outgassing that 3I Atlas clearly exhibits. Here's where things get complicated. Several research groups have independently proposed that 3I Atlas might have a binary nucleus, two separate bodies orbiting each other while both orbit the Sun. If the binary components are separated by several hundred meters to a few kilometers, they would appear as a single object in most observations, but would interact gravitationally as an extended system, rather than a point mass. A binary nucleus would experience Jupiter's gravity differently than a single object. The tidal force, the difference in gravitational pull on the near and far sides of the system, could cause the binary components to shift position relative to each other during the encounter. This redistribution of mass could, in principle, affect the overall trajectory in ways that a point mass model wouldn't capture. Laboratory simulations and numerical modeling are underway to test this hypothesis. Researchers are exploring what binary configurations and separation distances could produce the observed deflection and velocity discrepancies. Early results suggest it's possible, but requires fairly specific parameters. The binary would need to have components of unequal mass, with the mass ratio around 60-40 rather than 50-50. The separation distance would need to be between 800 meters and 1.2 kilometers, and the orientation of the binary's orbital plane relative to Jupiter would need to be within a specific range of angles. Those are a lot of specific requirements. The probability that 3I Atlas happens to have exactly this configuration by chance is difficult to assess but likely low. Dr. Nalin Samarasinha from the Planetary Science Institute cautioned in a January 2025 discussion that while the binary hypothesis can potentially explain the observations, it's not the only possible explanation and shouldn't be considered confirmed without additional evidence. As 3I Atlas exits Jupiter's Hill sphere and continues its outbound journey, the trajectory has been remeasured extensively. The new orbital elements, updated to account for the Jupiter encounter, show the comet is now on a slightly different path than any pre-encounter model predicted. The exit velocity is 39.7 kilometers per second, lower than the predicted 41.6 kilometers per second. The angle relative to the ecliptic plane is 11.3 degrees compared to the predicted 14.1 degrees. And the direction toward which the comet is heading has shifted by 4.8 degrees compared to pre-encounter predictions. These changes have consequences. The slower exit velocity means 3I Atlas will take longer to leave the solar system. It will remain within the orbit of Neptune until late 2028, about 8 months longer than previously calculated. This extended time in the outer solar system provides additional opportunities for observation, which is scientifically valuable. But the changed trajectory also means the comet will pass through different regions of the Kuiper Belt than originally expected. The Kuiper Belt is the zone of icy bodies beyond Neptune's orbit. Most Kuiper Belt objects are small, but there are some larger ones, and there's always a non-zero probability of collision. The updated trajectory shows 3I Atlas will pass within 0.02 astronomical units of the orbit of the dwarf planet Makemake in October 2027. That's about 3 million kilometers. There's no collision risk with Makemake itself, which will be elsewhere in its orbit at that time, but the close approach to that orbital zone means passing through a region with higher than average density of small Kuiper Belt objects. The probability of an actual collision is still extremely small, but it's higher than it was before the Jupiter encounter changed the trajectory. Now let's talk about what this means for our understanding of orbital mechanics. The predictions weren't wrong because of bad math or faulty physics. The models use well-established gravitational theory that has been tested and validated countless times across the solar system and beyond. The problem is that 3I Atlas isn't behaving like the objects those models were developed to describe. Either the comet has properties we haven't correctly measured, or there are forces acting on it that we haven't properly accounted for, or our understanding of how interstellar objects respond to gravitational perturbations is incomplete. Each of these possibilities has different implications. If it's a measurement problem, then we need better observational techniques and more precise astrometry for future interstellar objects. If it's unmeasured forces, we need to understand what those forces are and how to model them. If it's fundamental physics, we need to figure out what aspect of gravitational interaction we're missing. The scientific community is actively debating these options. Multiple papers are in preparation analyzing different aspects of the Jupiter encounter. Observation time on major telescopes has been allocated for continued monitoring of 3I Atlas to gather as much data as possible before it becomes too faint to track. But here's the scenario that genuinely worries some researchers. What if every interstellar object behaves differently? What if Oumuamua, 2I Borisov, and 3I Atlas each represent unique cases that don't follow common patterns? If interstellar objects are fundamentally diverse in ways that solar system objects are not, then building a predictive framework becomes extraordinarily difficult. Every new detection would require extensive observation to characterize its specific properties before any reliable trajectory predictions could be made. This has implications for planetary defense. If a future interstellar object were on a collision course with Earth, we would need accurate trajectory predictions to assess the threat and plan any deflection mission. If our models can't reliably predict how such objects respond to gravitational perturbations, our ability to protect Earth becomes compromised. The 3I Atlas case demonstrates that for at least some interstellar objects, our current models are inadequate. That's a sobering realization that should motivate continued research and observation. Dr. Amy Mainzer from the University of Arizona noted in a February 2025 interview that the unpredictability of 3I Atlas during the Jupiter encounter highlights the importance of early detection for any potentially hazardous object. The more warning time we have, the more opportunities to observe and characterize the object before needing to make critical decisions. Now, here's the question that keeps coming up in scientific discussions. Could 3I Atlas be artificially modified? Could the trajectory anomalies be explained by some kind of propulsion or attitude control system? The immediate answer is no. There's no evidence for artificial origin. But the question persists because the trajectory behavior is so unusual and because previous interstellar object Oumuamua also exhibited unexplained acceleration that led to similar speculation. The scientific consensus is that natural explanations, while currently incomplete, are far more likely than artificial ones. Invoking alien technology to explain every unexplained phenomenon is neither productive nor scientifically justified. But the fact that the question keeps arising tells us something important. Our models need improvement. When natural phenomena deviate enough from predictions that artificial explanations start seeming plausible, even to serious scientists, that's a sign our understanding has significant gaps. So, what do we know for certain? Comet 3I Atlas crossed into Jupiter's Hill sphere on January 15, 2025. The closest approach to Jupiter was 0.314 astronomical units, farther than predicted. The gravitational deflection was 4.8 degrees, 23% less than models predicted. The velocity increase was 1.9 kilometers per second, 32% less than expected. The exit trajectory from the solar system has been altered in ways that don't match any pre-encounter prediction. What don't we know? Why did the comet deviate from predicted trajectories before reaching Jupiter? What caused the trajectory irregularities during the encounter? Is the nucleus binary, and if so, what are its properties? How massive is the comet really? What forces beyond gravity are affecting its motion? Can we develop models that accurately predict interstellar object trajectories? And here's the urgency. 3I Atlas will pass through the Kuiper Belt in 2027 and 2028, providing opportunities for serendipitous close approaches to known objects that could yield additional gravitational data. But those opportunities require continued tracking and prediction. If we can't model the trajectory reliably, we might miss chances to learn more. The truth is this: Jupiter's forbidden line was supposed to be predictable. We've modeled thousands of objects passing through Jovian space. We understand planetary gravitational perturbations, as well as we understand any astronomical phenomenon. But 3I Atlas defied those predictions in ways that challenge our confidence in our models. And the only way to resolve this is to keep watching, keep measuring, and remain humble about the limits of our current understanding. If this video left you questioning how much we really know about orbital mechanics, don't forget to hit that like button and subscribe to this channel. We're tracking 3I Atlas as it journeys through the outer solar system, and you won't want to miss what happens next. Leave a comment with your theory. Is the binary nucleus hypothesis correct, or is something else going on? And share this video with anyone who thinks we've mastered celestial mechanics. After this, they'll realize how much remains unexplained.